Heating effect of electric current. Whenever the electric current is passed through a conductor, it becomes hot after some time. This means that the electric energy is being converted into heat energy. The particular effect is known as the heating effect of electric current. It is also known as ohmic heating or resistive heating, as well as Joule heating effect, named after British physicist James Prescott Joule, who established the relationship between heat energy and the work done. The effect is practically being used in a large number of commonly used electrical heating appliances, such as electric bulbs, room heaters, geysers, electric irons, and so on. The generation of heat in a conductor is a most common and unique effect of electric current. When an electric current passes through a conductor, it generates heat due to the resistance it offers to the flow of current. The work done to overcome the resistance is generated as heat energy. This way, the electrical energy is converted into heat energy. This is known as heating effect of electric current. The heating effect of current was studied experimentally in 1841 by Joule. He immersed a conducting wire of fixed length in a fixed quantity of water and passed a known amount of current through it. He measured the rise in temperature of the water due to the electric current flowing through the wire for a particular time period. By varying the current, length of the wire, and the duration for which current flows through the circuit, he concluded that the amount of heat produced by an electric conductor or a device. Do you know the cause of heating effect of current? When a potential difference is applied across the ends of a conductor, an electric field is set up across its ends. The large numbers of free electrons present in the conductor get accelerated towards the positive end, that is, in a direction opposite to the direction of electric field applied, and acquire kinetic energy in addition to their own kinetic energy due to their thermal motion, due to which an electric current flows through the conductor. These accelerated electrons on their way suffer frequent collisions with the ions or atoms of the conductor and transfer their gained kinetic energy to them. As a result of it, the average kinetic energy of vibration of the ions or atoms of the conductor rises, and consequently the temperature of the conductor rises or it gets heated. When a strong current flows through a conductor for a long duration, heat energy is produced in the conductor. We know that to sustain the current or the flow of charges in a circuit, a constant potential difference is always maintained across the two ends of the conductor. Since electric potential difference between the 2 points is the amount of work done in bringing a unit positive charge from one point to another point without any acceleration. Thereby, electric potential difference can be defined as the ratio of work done and the charge. In pushing a charge through the conductor, this amount of work done appears as the heat energy of the conductor. Heating effect of electric current. Whenever the electric current is passed through a conductor, it becomes hot after some time. This means that the electric energy is being converted into heat energy. The particular effect is known as the heating effect of electric current. It is also known as ohmic heating or resistive heat. Let us consider a conductor of resistance R and V be the potential difference applied across the ends of the conductor. If I is the current flowing through the conductor for time t, then the total charge flowing through the conductor in time t is equal to the product of current and the time duration. Hence, total work done in carrying a charge q from one end of conductor to the other end through potential difference V is equal to the product of the potential difference and the charge, which is also equal to V into I into T. Using the Ohm's law, it comes out to be I square R into T. This is the electric work done which appears as heat. Therefore, the amount of heat produced by the current also becomes equal to I square R into T. Since the SI unit of work is joule, same is the unit for heat energy. Heat energy is also measured in calories, and that can be obtained by dividing the value in joule by 4.18, as 1 calorie is equal to 4.18 joules. Physicist James Prescott Joule, who established the relationship between heat energy and the work done. The effect is practically being used in a large number of commonly used electrical heating appliances, such as electric bulbs, room heaters, geysers, electric irons, and so on. This equation is a mathematical statement of Joule's law of heating. Thus, Joule's law of heating states that the amount of heat produced in a given conductor when current flows through it for a fixed time is directly proportional to the square of the current flowing through the conductor. It implies that if the current is doubled, the heat produced will be 4 times, or if the current is halved, the heat produced will be 1/4. Heat produced is directly proportional to the resistance of the conductor for a given current and time. It implies that if the length of the conductor is doubled, that is, its resistance is doubled, the heat produced will also be doubled, or if the resistance is halved, the heat produced will also be halved. If the area of cross-section of the conductor is doubled, that is, its resistance becomes halved, then the heat produced will be halved. Further, heat produced is directly proportional to the time for which the current is passed through a given conductor and current. It implies that if the time for the flow of current is doubled, the heat produced will also be doubled, or if the time is halved. Let's take 2 charged spheres with different potentials on them. When they are connected by a conducting rod, the charge flows from the sphere of higher potential to the one with a lower potential. Here, it can be noticed that the charges continue to flow until the potentials on the two become equal. This shows that it is more meaningful to talk about the potential difference between 2 points in electric field region than the potential at one point. The actual value of the potential at any given point is not significant. Potential difference between 2 points is referred to as voltage. The SI unit of potential difference is volt. The unit is named after Italian physicist Alessandro Volta. 1 volt can be defined as the potential difference between any 2 points in an electric field is said to be 1 volt. When 1 joule of work is done in moving a positive charge of 1 coulomb from one point to the other against the electrostatic force of the field. In a simple circuit, it can be noticed that source of electrical energy, such as a cell or a battery, has location of high and low potential. Charge moving through the wires of the circuit will encounter changes in electrical potential as it traverses the circuit. Within a cell or a battery, there is an electric field established between the two terminals directed from the positive terminal towards the negative terminal. To move a positive charge through the cell from its negative terminal to the positive terminal, some energy is required that increases the potential energy of every positive charge. Here, chemical energy of the cell is used to do work on a positive charge to move it from the negative terminal to the positive terminal. It can be seen as the movement of a positive charge against the electric field. Because of this reason, positive terminal is described as the high potential terminal and negative terminal is described as the low potential terminal. Therefore, term voltage is also associated with sources of electrical energy. Let's see an example of electric potential and potential difference around us in nature. Do you know the cause of lightning? It is due to opposite charges developed on two clouds during their movement in the atmosphere. The cloud with a positive charge is the one with a higher potential, whereas the cloud with the negative charge on it is the one with a lower potential on it. When these two clouds come close to each other, the charges flow from the cloud of higher potential to the cloud of lower potential despite an insulating layer of air between them. The overheating of the layer of air and its sudden expansion causes a loud thunderous sound as well as a huge spark. The same thing may also happen between a charged cloud and the ground. Ionosphere in our atmosphere is another example of an extremely high potential. Electromagnetic induction. We know that if electrical current is flowing in a conductor, there is an associated magnetic field created around the conductor. In a similar way, if we move a magnet near a conducting wire, there should be an electrical current that will be generated in the wire. The phenomenon by virtue of which an electric current is induced in a conductor due to changing magnetic field is called electromagnetic induction. It is an extremely useful phenomenon with a wide variety of applications and used in power generation and power transmission. In 1831, British scientist Michael Faraday, an American scientist, Joseph Henry, introduced the concept of electromagnetic induction individually. But the credit of the discovery of electromagnetic induction goes to Faraday, because Faraday performed numerous experiments to prove that electricity could be generated from magnetism. He not only had clearly demonstrated the phenomenon of electromagnetic induction, but also had developed a good understanding of the processes involved. He hypothesized that whenever there is a change in the magnetic field lines linked with a conductor, an electric current is induced in the conductor, and the current is called induced current. Equal. This shows that it is more meaningful to talk about the potential difference between 2 points in electric field region than the potential at one point. The actual value of the potential at any given point is not significant. In his experiment, Faraday took a permanent magnet and a galvanometer connected to the two ends of a coil of copper wire. He observed when a bar magnet is moved back and forth inside the coil, there is a deflection in the galvanometer that indicates a current is produced in the coil, and no deflection of the galvanometer is seen when a bar magnet is stationary. That is, a moving magnetic field is necessary for electromagnetic induction to occur. Do you know the cause of the induced current in the coil? The basic cause of electric current is the potential difference or the electromotive force across the conductor. Due to the motion of the magnet with respect to the coil, an electromotive force is developed between the ends of the conductor. Thereby, an electric current is induced in the conductor. In general, whenever a coil of conducting wire is placed inside a magnetic field, a magnetic flux is linked with the coil. When the magnetic flux linked with the coil is changed, an electric current starts flowing in the coil. The current and the electromotive force so produced are called induced current and induced electromotive force, or induced potential difference. Do you have any idea how we can change the flux over a period of time? Magnetic flux can be changed by moving either the magnet or the conductor away or towards the other. In other words, if there is a relative motion between the conductor and the magnet. It can also be changed by increasing or decreasing the area. Another way to change the magnetic flux is by changing the orientation of the magnetic field. This is generally done by rotating the conducting wire along an axis that is perpendicular to the field. Let us make a motor. Take a 1.5 volt torch battery, 1 meter of insulated copper wire used for motor rewinding, 1 magnet, 2 metal file clips, 2 1 centimeter wide rubber bands cut from an old bicycle tube, some thread and ordinary hand. Using the Ohm's law, expression for the heat produced by a conductor can be modified as shown. For more understanding, let us try some numerical problems. An immersion water heater of resistance 500 ohm is connected to the main supply of 220 volt. Measure the heat produced in 30 minutes. Here, the resistance is 500 ohm. Time of flow of current is 30 minutes. That is 1800 seconds, and the potential difference is 220 volt. By using the appropriate relation, heat energy produced by the immersion rod comes out to be 174.24 kilojoules. In terms of calories, it comes out to be 41.684 kilocalories. In our daily life, we have many devices based on heating effect of electric current, such as electric heater, electric immersion water heater, and electric iron. All of these devices have a heating element or a metallic coil like filament that has high resistance and high melting point. An electric bulb is also based on heating effect of current. It emits light when the filament of the bulb becomes very hot. To generate the heat as much as is possible, metals with high melting point are used as filament such as tungsten. However, to prolong the life of filament, electric bulbs are usually filled with chemically inactive gases like nitrogen and argon. Another application of heating effect of current is in thermostats. Bimetallic strips are commonly used as an automatic switch in electrical heating devices, such as electric iron, electric kettle, etc. A bimetallic strip consists of two strips of different materials, such as brass and iron, but of equal length, placed back to back so that they cannot move separately and riveted together at different points along their lengths, such that they cannot slip sideways. When the bimetallic strip is cooled or heated up, it bends. This principle is used in fire alarms and thermostats to break the circuit. A thermostat is used for maintaining a steady temperature. Its job is to turn something on or off. An electric fuse used in electric circuit is also an example for the application of heating effect of current. It consists of an insulating body that holds a replaceable thin metal wire connected between two terminals, whose melting point is lower than the melting point of rest of the wiring system. This is how it is symbolically represented in a circuit diagram. Whenever there is an excessive amount of current in the circuit due to short circuiting, overloading or a sudden supply of high voltage, it results in a lot of heat generation, causing damage to the wiring. A fuse is a big respite in this situation, as the fuse wire melts to disrupt the excessive flow of current and thereby prevents the circuit and its components from getting damaged. Look at a simple circuit with a bulb that does not contain a fuse. There is overheating in the circuit and the bulb is blown off. If a fuse is introduced in the circuit, it will blow off instead of the bulb in case of overheating. This is why a fuse is a compulsory element of every circuit. Today, a replaceable fuse, that is, a cartridge fuse, is in use. When the fuse is blown off, it is replaced, rather replacing its wire. Such types of fuses are used for domestic purposes and rated as 1 ampere, 2 ampere, 3 ampere, 5 ampere and so on. Rated value of an electric fuse indicates the maximum current it can sustain. For example, an electric iron, when operated at 220 volt, a current of 4.54 ampere flows through it. In this case, a fuse rated as 5. The value of electrical resistivity varies over a wide range for different materials. In general, electrical resistivity is very low for conductors and very high for insulators. However, substances having their electrical resistivity between that of conductors and insulators are called semiconductors. Copper and aluminium have a very low electrical resistivity. That is why they are commonly used for making electrical wires. However, the resistivity of silver is too low that it can be used as the best conductor of electricity. While electrical resistivity of alloys like manganese and constantan is very high. Thereby, thin wires of these materials are used to make standard resistances. Do you know that the filament of an electric bulb is made of thin tungsten wire? Because tungsten has high resistance, as well it oxidizes at very high temperature. For most of the metals, the resistivity increases linearly with increase in temperature over a temperature range of about 500 Kelvin above the room temperature. For semiconductors, resistivity decreases with temperature, and for the insulators, the resistivity increases exponentially with decrease in temperature. It becomes infinitely large at temperatures near absolute zero. It is clear that the resistance of a conductor depends upon its dimensions, that is, length and area of cross-section, its nature and its temperature. And the resistivity depends on nature and the temperature of the material, but independent of the dimensions of the conductor. Also, resistance is a property of an object, while resistivity is a property of the material. Let's try some numerical problems on resistance and resistivity. Calculate the resistance of a wire of length 1 millimeter and area of cross-section of 4 millimeter square. Resistivity of the material of the wire is 1.5 into 10 to the power minus 8 ohm meter. Here, the resistance comes out to be 3.75 into 10 to the power minus 6 ohms. Next problem, a wire of given material having length D and area of cross-section A has a resistance of 20 ohms. What would be the resistance of another wire of the same material having length D by 2 and area of cross-section 2A? Here, the resistance becomes 5 ohm. In this problem, a wire of given material having length D and area of cross-section A has a resistance of 1 ohm. What would be the resistance of another wire of the same material having length 2D and area of cross-section A? Here, the resistance becomes 2 ohm.